Okay, folks. So we're going to pick up where we left off. Inductive effects. Woo! Okay, so remember that when you have an electronegative atom, that's going to pull electrons through the bond that's attached to, right? Or another way of saying that is that's what a bond is, isn't it? Okay? It's literally the two sharing electrons. If one of them is more electronegative, then it's going to pull electron density towards it, isn't it? Okay? So again, the presence of nearby electronegative atoms is going to increase the stability of a conjugate base. This is because it can pull electron density away. And so we see two examples here. We see an ethoxide here, see that? And because of the extra electron density, the carbon's going to have a bit more electron density than it normally would, right? Because the oxygen's going to be overloaded, okay? Over here, though, we see another ethoxide, but this one has a chlorine over here. Can you see that okay? Okay. And so what's going to happen is some of this electron density, see that? Is going to get pulled through the bond series towards that chlorine. Think of them as little tiny wires because that's ultimately kind of what they are, aren't they? Okay? And you can pull some of the electron density through that series of bonds. Okay? Now, you're going to have a very limited amount of space, spatially. This is going to have a very limited effect, right? Does everybody understand what I'm saying when I'm saying spatially this has a limited effect? Okay. Think of it a bit like this. If one of you was pulling on one of your neighbor's arms and the other's pulling on the other arm, is adding another person on the other side going to have as much effect as the immediate? No, because they can't get a good grip, right? So it's going to have tremendously reduced effect, each link in the chain, isn't it? Okay? And that's the same thing we're seeing here. But you can see there's actually a fairly significant effect being one carbon down from that first carbon, right? Okay. Everybody good so far? Okay, and this is called the inductive effect. This is the same as the inductive effect for magnetic fields, the inductive effect for electricity. Okay? It's actually the same root cause. Okay? We just have to remember that in this case we have atoms. So there's a very limited electron mobility because you have little nuclei that you have to pass around, right? Yeah. Okay, so this is, again, the inductive effect in anions, and this is just showing you this effect in a nice straight chain so it's easier to see. Is everybody okay with that? Okay, fantastic. Okay. All right, and what about positive charges, by the way? What would happen to a positive charge with something very electronegative a little bit down the chain? It's going to destabilize it, isn't it? Yeah, because we're pulling electron density that we need, right? Yeah. So it's going to make it even more positive over there. Okay? And that's, of course, going to destabilize it, just like we predicted. Okay. This right here is electron donating groups. This would be the opposite, same inductive effect, but now we're looking at donating electron density. Okay? One of the big ones you're going to see this for is hydrogens when we're talking about nonmetals. Okay? We will have some examples of metals, though, as well. Okay? However, in this course, because we're organic chemistry, we're only going to do very limited metallic groups. Okay? It's very, very rare. Very unusual. But if anybody's taken inorganic chemistry with me, which is going to be next semester, if anybody needs that, which I know a few of you do, that's usually the chemistry majors that take that, we will actually get a lot more into this, okay, in using metals and these things. Yes, metals can make covalent bonds. Yes, you can do all sorts of stuff with metals. A lot of the general chemistry stuff we taught you, super simplified, not complete in any manner, okay? Okay, now this is again those bond dipoles. Remember we talked about bond dipoles and we were usually adding them up and figuring out the molecular dipoles, right? But those bond dipoles also told you that electron density was getting concentrated in this carbon. You see that? So if we attach that carbon with 3 hydrogens around it, this can have an inductive effect where it's going to load up electron density to the next group. See, that's electron rich. Okay, and that's an electron donation, of course. So if we were to attach these to something that's already negative, like an anion, this is going to destabilize them, right? If we attach it to something positive, what is that going to do? Stabilize it. Very good. Okay, and so that's a electron donating group. The other ones that we were talking about, these would have been electron withdrawing groups, okay, because they withdraw electron density. Okay. All right. This is the summary of everything we just talked about, in case you forget everything I just said and, just want to quickly get a slide. All right. There's also the videos, of course. That's faster, though. All right, so let's talk about some strategies for success, ranking acids and base strength by using the cardinal rule. So with few exceptions, the order of priority for charge stability factors follows the cardin, and then we put AL to make it a complete word that makes some sort of sense to us. Okay? Everybody ready for it? Okay. All right, so charge is the first one. Atom is the next one. Resonance delocalization is the one after that. And then inductive effects is after that. And then we add AL just to make it sound nice. Okay. Everybody good with that? Okay. I'm honestly split on whether these help people or not. These like catchy slogans. The data actually shows that they don't particularly help. That the people that actually they benefit would have memorized it anyways. It doesn't matter at all. Yeah. But we'll try, okay? It's something I can try. So do the species have different charges? A charged species is going to be more reactive than one that bears no formal charge. Everybody remembers formal charges? Okay, fantastic. Do the charges appear on different atoms? So your size, electronegativity, hybridization of the atom on which the charge is located is going to affect your stability. Are the charges delocalized differently through resonance? More resonant structures you have, the more you can share that charge, right? And the more stable it's going to become. Okay. Are there differences in inductive effects? If you have electron withdrawing groups, that's going to help stabilize any nearby electron-rich groups, right? Or another way of saying that is anions. Okay. If we have any electron donating groups, it's going to stabilize your positive ones because it's going to give a bit more electron density to anything nearby. Okay. And vice versa. It'll destabilize the opposite, right? Okay. This is actually a summary of these rules with a little bit of pKa differences that we can see the effects. Okay? And you see how the charge of the atom is the big effect, right? Because remember, that one's going to be changing whole charges. To me, that's the easier way to remember that, by the way, is how much of a difference does it make on the charge? And a +1 or -1 makes a whole charge difference, right? The atom type, on the other hand, is going to be the next one. And this is going to have the next largest effect. It's a pretty large effect, though. Okay? And you can remember this very large effect because of the things like HCl versus HF, right? Versus H2O. The atom type there has massive effects. Okay? The next one is the resonance delocalization. Now we're getting into stuff that has kind of minor effects. Okay? For example, carboxylic acids, none of them are strong acids, are they? They're all delocalized, but you have no strong acids being caused by that. And so it's a relatively moderate effect. Okay? Then you have the inductive effects. These can add up. You can actually get them to add up pretty significantly. But individually, the inductive effects are going to be your smallest ones. Okay? Mm-hmm.
Is the atom type, is that influenced by stuff like electronegativity?
Mm-hmm.
Okay.
Yep. Yeah. That's actually one of the biggest causes of that. And that's actually what you're seeing in this oxygen versus the nitrogen here. Mm-hmm. Yeah. And this one right here is actually bond character, yeah, which effectively is an electronegativity differential. Okay, you can do it as an effective electronegativity difference. That's what those slides were. What I was saying is like effectively having a more electronegative atom. Okay, so let's go ahead and rank these and try to predict. So, can we apply the cardinal rules to rank the strengths of these 4 acids? Rank me these 4 acids. What's going to be the most acidic? Okay. Okay. See, that'd make a lot of sense. What's the next one? D. Okay, that would be a pretty significant acid. Yep. How about the next one after that? B. Yeah. Why is that? 2, 3. 1, 2, 3, 4. Right? Yeah. So we have an electron withdrawing group that's closer, don't we? Yeah. The other one, on the other hand, is a bit further away. Okay. Okay. Cool. And these are those acid strengths and where you can locate them, by the way. Mm-hmm.
So what was the order? It was C was the strongest.
This is actually where it shows you right here. This one's actually somewhat of an unusual case here. And the reason for that is that this right here is creating the same group on both sides. So that's why that actually flips. But yes, you're correct. The cardinal rule would say this one would normally be the more acidic. Okay? However, because we have the same species right there, we actually don't have a significant difference in energies here. Okay? Which does mean it's the most acidic, yes, but it's kind of an interesting case of this. Okay? On the other hand, the rest of these are actually weak acids. And so you would have relatively little of these that would actually come apart. And so your strongest acid right here, this is your next strongest, this is your next strongest. Okay? Okay. So we were correct in the ordering. I just wanted to point out that this is kind of a unique case, which is quite interesting. The rest of these are energetically almost equivalent for the reactants. It's only the stability of their products that makes a difference. Yeah. Okay, and that's actually the ordering, by the way. Yeah. Which is the same as this ordering here, but yeah. Okay. Let's look at the conjugate base strengths. If we look at the conjugate base strengths, the stronger the conjugate base, then the what for the acid? Is it stronger or weaker?
Weaker.
Weaker, yeah. Stronger conjugate base means weaker acid, right? Fantastic. Yeah. Very good. Okay, so let's talk about this in a physiological sense, since this has a large applications in physiology. Okay, I think you guys actually do this in micro. Has anybody done micro? Yeah? Yeah, you do a little bit of like pH with the amino acid stuff, if I remember correctly. Anyways, if you're taking biochemistry, you'll end up doing this a fair amount. This becomes quite important, actually. So when we look at an amino acid, what we can see is we have an amine group here, and we have a carboxylic acid here, and then we have right here the side chain. That's the one that determines whether this is glycine or lysine or whatever, right? Okay. The side chains do not actually necessarily have acidity or basicity that's significant in this case. Okay? Some of them do, some of them do not. But right here we have the amine and we have the carboxylic acid. Carboxylic acid is a acid. The amine is a base. And so what happens when you put this in water? Yeah, this deprotonates, right? And this gets an extra H, doesn't it? Plus, minus. Okay? So typically when you put an amino acid in water, it actually self-deprotonates and reacts with itself, okay, as an acid and base. Okay, so the pH of the solution actually determines which form you're going to have for this. Neutral solutions that are like water, we're going to have this form right here. Anybody know what that's called? Zwitterion. Okay, do you know how to remember that? It says it right there, but Zweihander. Anybody heard of Zweihander before? No? Okay. If you ever go to a museum, that's the two-handed swords. And two-handed's why. It's German. All right. So Zwitterion, two ion. Okay? Has a positive and negative end. It's neutral overall in this case. So the overall charge is going to be neutral. We'll have a net charge of 0. And we will have one end that's positive, one end that's negative. And again, that is the Zwitterion. Okay? Okay, what if we go ahead and get a pH that's higher than what this acidity would be right here? Yeah, we're going to end up protonating that, aren't we? And that's going to go back to base because it will react with whatever base is in the solution. Okay? And in most of these, it's going to be a pH that's significantly higher than 9. Okay? Typically somewhere in the 10-ish range for most of these, though there's some that are a little bit lower. Okay? The pHs between 2 and 9 typically are going to have your Zwitterions for these, though if there's a charged side chain, that may actually change that. Okay? And then the pHs below 2 are typically where you're going to reprotonate the carboxylic acid, because carboxylic acid is not that strong of an acid. Okay? It's actually a weak acid, right? Okay. By the way, is there an application to this that we could use? What if we wanted to separate different amino acids? Is there some way we could use that? Yeah, we could change the pH solution. Remember how we separated a acid impurity? So if you very carefully changed your pHs, you could change what's a neutral species, right? Yeah. And you can actually separate them based on their polarities, can't you? Yeah. So there are applications to these beyond just, hey, interesting fact. Okay. All right. This is, again, the ionizable side chain here, and we see that we have a carboxylic acid on the side there. And so the Zwitterion species actually has to protonate one of the OH groups for it to be a Zwitterion. Okay? If we're actually pH 3.86 in this case to 9.82, we're actually going to end up with a -1 charge overall. And that's not a Zwitterion. Okay? Everybody good with that so far? Okay, fantastic. All right, this is actually lysine. And so in this case, our Zwitterion is right here because that doesn't have a charge, and this one has the positive charge. Everybody see that all right? Okay. And if we get in between pH 2.18 and pH 8.95, we actually end up with an overall positive charge. Okay. Okay, anybody have any questions about those so far? No? All right, that's actually the end of it. We're going to go on to the next one. Ooh, we are covering material. I know. No questions overall?
Did we look at some of the questions in the homework for this chapter?
Send me in questions. I'll make videos or answer them in person.